All right, thank you for this opportunity to present my paper. It's unfortunate that I couldn't join you. I was looking forward to going to Scotland, but something came up. My paper is entitled, Whose Baseline Compiler Is It Anyway? So first of all, what is WebAssembly? It's a low-level binary code format first introduced for the web in 2017. It's a compilation target, so you don't write WebAssembly by hand. It runs at near native speeds, and it's now being applied to many other domains, not just the web. In particular, this is a quote that I've been trying to spread. WebAssembly will be like Unicode. There are things that I don't like about Unicode. It's not perfect, but the one standard for compiled executable code. That means that I think that work on WebAssembly will be high impact. Let's talk about executing code. There are effectively three categories of execution tiers. The lowest or the slowest is interpreters. So we are dynamically decoding a data structure, maybe bytecode to execute a program. A key thing here that distinguishes an interpreter from everything else is that an interpreter operates without generating any new machine code. And so that means that it needs little to no processing of the code and therefore is ideal for fast startup. The middle tier is a baseline compiler. So by this, I mean a compiler that does not build an IR. And that typically means that you do little to no optimization in a baseline compiler design. It's often single pass and can be based on templates. Optimizing compilers are the highest tier. They generate code by building and optimizing an IR, and they use the traditional textbook compiler techniques, and they generate the highest quality code. VMs that have to dynamically load code, so they have no opportunity to compile the code offline, they often trade these tiers off for better overall performance. For example, using an interpreter to start executing code that may be cold or executed only once, and then optimizing later as code is detected to be hot. So if we looked at that pictorially, this is an image from a paper from a couple of years ago that I wrote. This is actually WebAssembly execution tiers as measured on two dimensions. One is the startup time or the processing code per byte, and then the other dimension is the execution time. And you can see there's very clear categories and delineations between them, with optimizing compilers being in one corner and interpreters being in another corner. This paper is about Wizards JIT, which is a baseline compiler, which fits right about here in this trade-off space. How do we get there? So this is about the middle tier. So we're talking about baseline compilers. And the interesting thing about baseline compilers is that they're very much benefiting from WebAssembly's design for fast code validation. WebAssembly is a stack machine. It has structured control flow. That means that blocks and loops are actually nested and they have to pre-declare their labels. It doesn't require a lot of type inference. In fact, all the local types are basically already there. If you read the specification, it looks like a type system, but actually real implementations use abstract interpretation. And that basically means they have two data structures. One is an operand stack and one is a control stack. Similarly, fast compilation of WASM and baseline compilers that exist is done basically the same way. There's an operand stack and a control stack. Both V8 and SpiderMonkey actually reuse the core visitor in their validator for baseline compilation. The key trick is that we need to over-approximate the abstract state at loop headers so that we don't actually have to run a fixed point so that it's still fast. The basic data structure for the operand stack is augmented with some information for register allocation. Register allocation is super important to get good code, but we can also do other optimizations. We can do constant propagation, constant and branch folding, instruction selection, people optimizations, and of course, register allocation. It's possible to do other forward pass optimizations. I didn't explore them, but did think carefully about whether it's possible. I think it's possible to do loop peeling, common sub-expression elimination, and definitely null check elimination. So there are a couple of design constraints for Wizard. In particular, the top priority is observability. So having a VM where you can actually do dynamic analysis of programs and debug programs. So one of the innovations here is that Wizard has an in-place interpreter that allows you to do instrumentation. I wrote a paper about that last year. A key thing here is that the value stack actually has these different possible value representations, notice that each of them has a dynamic value tag. That's some type information that distinguishes a reference from a primitive. That's a key design constraint. We'll see in a minute that actually Wizard's baseline compiler actually has pretty much the same frame layout, and that allows it to transfer between the two quite seamlessly. So Wizard's JIT is a new state-of-the-art single-pass compiler. It does optimizations such as constant propagation folding, instruction selection, and register allocation all in one pass. As before, it does the same stack frame layout as the interpreter. That means that we can do constant time deopt in OSR to and from the interpreter. We're going to need to do some optimizations to improve the performance of those value tags. But the idea is that since we have the same stack frame layout, we can do dynamic optimization. And last but not least, it also supports instrumentation via probes. And that means that we can do full fidelity instrumentation and debugging because observability is the highest goal here. So it's pretty much all this diagram, this one diagram in the paper that explains how it works. Abstract interpretation is effectively you have an approximation of the state. And so the state here being the locals and operand stack. We've got some WASM code on the left. So that's the green. Obviously, WASM is a binary code, so we're showing the text format, so it's been disassembled. The thing in the middle is the important thing, is the abstract state. This is going to track whether a value has been stored into the stack in memory or not stored into the stack in memory, and also whether it's in a register and which register. On the right, we've got the machine code that comes out. So this is actually just a fairly simple loop that just counts down. This is going to be the actual machine code that came out of Wizard's baseline compiler. And we'll just step quickly through some of the operations that happened when this compilation went through. So first of all, the calling convention means that the arguments to this function come in memory. So they're in the value stack in memory. So they're already stored. We model them that way. And then this first instruction, local.get, effectively loads something out of memory into a register. So we allocate a register for it. And so we need to actually load it. So that's what this instruction came from. But notice the next instruction, which stores to a local variable, doesn't actually write anything to memory. And instead of it just manipulates the abstract state. So this register gets moved there. I mentioned that loops actually have to be pre-declared in WebAssembly. And since we want to use abstract interpretation without running to a fixed point, we're going to over-approximate the state. That means that there's one slight change from EAX being the register for two things to being just one thing, because the loop has to assume the worst case scenario, which means that something could be modified. And so something that was equivalent starting at the loop may not be equivalent coming back, so it can only be in one register. A register can only hold one thing. So that's what that means. And then when we continue with each instruction in sequence, we just model the register allocation. We also model constants. So this I32 const 1, that loads a constant onto the stack. That allows us later when we execute, emit code for this I32 sub to actually select a better instruction where we use an immediate. So notice there's a whole run of instructions that don't actually generate any machine code at all. And then we just keep trucking through this loop body here. And when we get to the branch that goes back, key thing here is that when we branch back to the header of the loop, we actually have to match the state that we had at the header of the loop. So the jump is going to have a one shuffle instruction here. This move here comes because we need to put the right value back into the right register. And then we just continue on and we generate code all the way to the end. And so that's the basics of how it works. Trust me, there's a lot of details in making all of this work and lots of fun debugging to be done. And of course, all the data structures, you have to make them quite efficient to make this run fast. So Wizard also supports instrumentation, and the way it does that is with a mechanism called local probes. Local probes are effectively a callback to user code that allows them to do programmable instrumentation at a location in the code when that location is executed. So in the interpreter, we can do that by overriding a byte with an illegal byte that will then call back to the user code so that the interpreter's execution handler will hit it. When we're compiling, we can just insert a call to the runtime at that location. Since we're doing single pass compilation, we don't need to put anything on the IR, so it's not that much work. And in fact, all the code before the probe instruction will be unaffected. You'll get exactly the same code. And then when we do hit this, we effectively are going to dump all the registers into memory and then call the runtime. For certain kinds of probes, though, like we may not want to call the runtime just to do an increment of a counter. So some kinds of specialized probes are known to the compiler and it will generate effectively intrinsic code. So in this case, if we had just had a counter, which is actually extremely common for instrumentation task, we can just emit the 2 instructions or 1 instruction necessary to implement the counter. So value tags are important because they distinguish reference values from non-references in the WASM value stack. They're really only used for garbage collection in Wizard, although there is some verification and debugging use cases too for value tags. But they're not actually needed for the execution of the WASM program because WASM is a statically typed bytecode. Other engines, when faced with this problem, would typically use stack maps. So their JIT compiler would emit a stack map that tells the stack walker exactly which words are references. There's some optimizations here, and I explored a few. One obviously would be to implement stack maps. There's reasons for not doing that. Obviously, we want to compile fast, so computing all of these stack maps is additional compilation work we want to avoid. Another way to do it is to compute those tags at GC time for metadata. So I call that lazy tags in the paper, and I evaluated that. But what Wizard does in its baseline compiler is on-demand tags. So as part of the abstract interpretation state for both the operands and the locals, we actually track the state of the tag to tell whether or not it's already been stored and whether it's been changed, and only update memory when necessary. So now I want to talk about some experiments in the paper where we evaluate the effectiveness of the compiler and these optimizations. So the first one is, does the JIT make things faster? And the answer is yes. Surprise. So I wanted to actually quantify the speed up from the JIT and quantify it under different optimization configurations. So the baseline here is going to be Wizard's interpreter. So 1.0 would be the same speed as the interpreter, and 5 would be 5 times faster than the interpreter. Use 3 different benchmark suites, PolyBench-C, Ostrich, and libsodium. And you can see that the speed up ranges anywhere from 5x to about 28x. And these error bars are not error bars in measurement. Those are actually the variance over the individual line items in the suite, with the bar height being the average over the suite. And you can see that 15 is actually very common to be an average speed up. And then if we look at the different configurations here, the different bars, the green bar is all optimizations turned on. No K is turning off the tracking of constants in the abstract state. No K fold is turning off constant folding, but still tracking them. No ICEL is the turning off instruction selection, so no like sub-Is and things like that. And then no MR is not allowing a register to hold more than one, a value to be in more than one register. And you can see actually it does make a difference. So there's almost a 3x difference here, or a difference of 15 to 12. That's about 20% in turning off the multiple register support. And over here, actually, tracking constants seems to be quite important. So those optimizations actually do matter, and I'm glad that I put them in. So the next thing, that I wanted to evaluate is, what about those value tags? Value tags are pure overhead. They don't actually help the WASM execution at all. So I evaluated the baseline here is, what if we just turn value tags off? So this is just the baseline compiler, no more interpreter. So 1.0 would be the same speed as having no value tags, including no dynamic instructions for them and no space. What if we always did the naive thing of storing the tags to memory? And that's about 3 times slower. So if you just did the naive thing, it would be 3 times slower than not having any value tags at all. If you were to do lazy tags, it's kind of on the order of 1%. Lazy tags has some disadvantages that I didn't want to implement that. The on-demand strategy, which is abstract interpretation based, is about the same as lazy tags. We're down to about 1%. So we're like within a hair's breadth of having no tags at all, except over here it's more like 5%. So what seems like a really expensive thing actually turns out not to be once you apply the on-demand optimizations. Okay, so there are many other baseline compilers out there for WASM. In fact, when I worked on V8, that was the first thing that we built after the optimizing tier was Liftoff, which is the baseline compiler in V8. SpiderMonkey also has a baseline compiler. Those both came out in about 2018. And there have been other engines that have baseline compilers. And I'm being very specific. I'm talking about baseline compilers that don't have an IR. There are other fast compilers that do have IRs. I left them out of this particular comparison because I only wanted to compare the baseline compilers. Compared two dimensions, one is execution time, one is compilation time. And so here the baseline is going to be Wizard. So anything which is higher than 1.0 is going to be slower than Wizard. And again, the variance here is going to be the variance in line items. It's not the measurement error. And so you can see over here, actually Wizard so happens to be faster than all of these on these particular benchmarks. It's not faster everywhere, trust me. And then in compilation time, Wizard is about the same speed as Liftoff in compilation time. And it's obviously, they're all faster than WA0. SpiderMonkey is remarkably fast in compilation time, almost 3 times faster than both Wizard and Liftoff. And this WASM Now, which is the copy and patch, is actually really fast. But unfortunately, it's not maintained, so it doesn't actually run all the benchmark suite. This is the same data, two-dimensional plot. You can see there's kind of clusters. It's a little bit messy, but you can kind of see there's some trends. I was also very interested in comparing and putting the baseline compilers in context with both interpreters and optimizing compilers. So this is probably the largest scale study of execution tiers for WASM, 18 different execution tiers, 12 engines, and I estimated the two dimensions again. I used a slightly different methodology. There's a little bit more noise in this data. I wish I could improve on that, maybe see the paper for what I'm talking about there. But we're looking at both execution time and startup time. And it's surprisingly messy data, but there are some trends here, which you can stare at in the paper. But this is it. So again, this is the speed to set up the module, so faster to the right. And this is the speed up over the baseline of interpreter. You can see there's an AOT compiler here, which basically uses LLVM, starts up very slowly, but generates very good code. There's WASM Now, which is the copy patch thing. Turns out that this actually has a fixed startup, which is not reported before. Interpreters are down here, interestingly. They do start up very fast, but they actually overlap a lot with these baseline compilers. And that's partly because code validation actually needs to happen too. And my methodology for studying that actually includes code validation. But you can see the bluish points are baseline compilers, purple and red are optimizing compilers, and you can see there's some clear blobs here and a little bit here, but the blue is kind of in there. So I think this is actually super interesting. We can now start to see like the trade-off between interpreters, baseline, and optimizing compilers in a visual way. And that's what this paper is all about. So thank you, and I'm happy to take questions if we have time.